So our next talker is Dilshan, also from UNSW, and take it away, Dilshan.
Thank you, Kane, for the introduction, and thank you everyone for joining today. So today I'll be talking about beautiful construction by Burns-Jones, something that Ryan already mentioned in the previous talk, which has many wide applications. So, for example, for constructing new groups with properties which have not been witnessed before, interesting group actions, and I'll be talking about a particular application of this construction, which is to construct irreducible representations of Thompson's groups. And the work I'll be talking about today is a joint work with my supervisor, Arno Godia. Okay, so to get started, I'll talk about Thompson groups. So if you were listening to the previous excellent talk by Ryan, we know all about the Thompson's groups, but just for the benefit of everyone, I'll just say a few quick words about it. So there's three Thompson groups, F, T, and V, introduced by Richard Thompson. And on the left here, we have an example of an element of F. It's piecewise linear. And usually, and while this is the most convenient way of viewing elements of F, a usually more convenient presentation, which is due to the work of Brown, is viewing them as a pair of binary trees or tree diagrams. And importantly, this association is not one-to-one. You can have many tree diagrams corresponding to the same element of F. So the larger Thompson groups, T and V, are defined in a similar manner. So for Thompson group T, we have the same thing going on, but we allow for cyclic permutations of the intervals of leaves, depending on the representation you're looking at. And for V, we allow for any kind of permutations. So I won't talk about any more technical details about the definition. It won't be too important for the talk. So why we want to study Thompson's groups? So as Ryan alluded to, it has many fascinating properties. However, quite interestingly, its analytical properties have been challenging experts for several decades. And one of the reasons why it's so challenging is that so little is known about its representation theory. And just one thing to note in this talk, whenever I talk about representations of groups, I will always mean unitary representations of groups acting on a complex Hilbert space. Okay, so it's important to understand the representations because many analytical properties of groups have equivalent formulations, or in fact were originally defined in terms of their representations. So this indicates in order to have a better handle or understand the analytical properties of F, we first need to understand its representations. So unfortunately, as you can probably guess from the heading here, this is easier said than done. The representations of F has been proven to be very challenging to study for several different reasons. So firstly, F is an infinite discrete group. Okay, so if you take a few steps back, I'm sure in any introductory course in representation theory, the first thing you will learn about is representations of finite groups. So in the land of finite groups, things are much simpler. You can easily find node representations and classify them. Okay? And then if you take a step further and go to the land of infinite groups, which have some nice topology, perhaps maybe compact or Lie groups. In this case, it is a bit more difficult, but there's still nice tools and techniques that we can use to study the representations. And in some cases, we know the representation quite well. So if we take a step further and go to the land of infinite discrete groups, so now things are much more difficult. So unfortunately here, there are no general techniques or tools that we can use to study the representations. You really have to go by case basis and really look at each of the representations to see what kind of tools may work. And in general, the representations for infinite discrete group, there are many in general, so you can't really say much statements in general. And just to give an indication of how difficult it can be, so the representation theory of the free group generated by two elements is essentially a mystery today. So that means no one knows how to classify two unitary matrices up to unitary conjugation. Okay, so that kind of indicates even for groups, it's going to be quite a difficult task. So that's quite a general statement. So if you talk more about F in particular, then we have this interesting fact here, which is that every irreducible representation of F is either one-dimensional or infinite dimensional. So what this means is if we ignore the one-dimensional ones, because those are going to be quite boring, okay? This means that if you want to study irreducible representations of F, we can't look at finite dimensional representations where we have a linear algebra and things are a bit easier. We actually have to always work in infinite dimensional spaces where it's much harder to work with. And just to give an indication of how difficult it can be. So the Koopman representation associated to the natural action of F on a unit interval. So this is a classical representation, which you can define for any group with a nice action on a measurable set, okay? So this representation was only shown to be irreducible in 2012 by Cuntz. So that's quite remarkable if you think about it. It took nearly 50 years for a proof to come to show that this representation, which is quite well known, to be irreducible. So these are quite difficult questions to try answer. So it's not all gloom and doom though. So there are known families of irreducible representations of F. So for example, there's a class of representations induced from the permutation representations of the Cuntz algebra. There are these Bernoulli representations, which were initially constructed by Cuntz and then later generalized by Olesen in his PhD thesis. So these families of representations, these Bernoulli representations, you can think of as being deformations of the Koopman representation. And we also have a family of Jones representations constructed by Jones coming from certain trivalent tensor categories. It's actually quite interesting for this last example here. Jones himself in the paper says that the proof for irreducibility and equivalence actually came from a remarkable piece of luck where it involved finding a certain element which had an invariant for each of the representations in the family. So here I have 3 examples of irreducible families of representations of F. And in fact, at least to my knowledge, these are the only known families of irreducible representations of F in the literature. So you can see there is not much known about the representation theory for F. Okay. So luckily though, thanks to the work of Jones, he had recently developed a powerful machinery to construct unitary representations of F. And really the whole underlying concept behind this machinery is how from simple objects, which are easy to understand, how can we build more complicated objects, which we are interested in studying, okay? And moreover, how from the properties of these simple objects, can we understand properties of these complicated objects, okay? And this is really going to be the underlying motive in my talk today. So that's something to try to keep in mind. And hopefully I'm able to show this concept well in what I show you today. So as I mentioned, there are many applications of Jones machinery. So I'll only be focusing on a very specific application, which is to construct what we call Pythagorean representations. And this initially came from a paper by Brothia and Jones in 2019. So in this application, our simple objects are what we're going to call P modules. So it's just a triple with 2 operators A and B acting on a Hilbert space, and they satisfy this relation here. Okay. And there's no restriction on the Hilbert space, but in general, in practice, we're going to make it finite dimensional. So that's going to keep things nice and simple. And I think we can all agree this is a relatively simple object. We can use finite linear algebra to study most of the properties. Okay. So from this P module, a simple object, using Jones machinery, we can construct what we call a Pythagorean representation of F acting on a larger Hilbert space. Okay, so you can think we have our P module, we feed it to our Jones machine or Jones machinery, and then out comes this Pythagorean representation that we want to study. That's what we're interested in studying. Okay, and I should mention, right now, from what I'm saying, it may sound very mysterious about this Jones machinery, but it's actually relatively quite simple to understand what's happening. It's really just a direct limit process, if you know what that is. And it's not actually a black box. You can actually see everything very explicitly and very diagrammatically as well. So it's quite, that's one of the kind of the main benefits of using this machinery. Some other notes, or some other important things to note is that this large Hilbert space that our representation acts on is always going to be infinite dimensional, okay? Which is good because if you think back to the previous slide, we know that the irreducible representations are always going to be infinite dimensional, okay? Moreover, these representations extend to the larger Thompson groups, T and V, and they also actually extend to the Cuntz algebra as well, which is nice. And just to give a quick snapshot of what this representation looks like, okay? So this is just an example. We have an element of F here on the left-hand side, a pair of trees. I have an element of my big Hilbert space here. So I haven't actually said what this Hilbert space is, but you can just think of it as space of all binary trees where the leaves have been decorated with elements in our little Hilbert space edge. So our starting Hilbert space, okay? And you may have noticed that I've drawn these like fractions, so that's not a coincidence. It's actually very similar to the actions that you saw with Ryan, with the forest king groups. So all you're going to do is you notice that the tree at the bottom and the tree at the top here are the same. So we can cut them out and we get our action here. So as I said, this is one of the benefits of Jones machinery where everything is very explicit and you can really easily see how the action works. Of course, there are many technical details behind it to make sure that this is actually a representation, but the end result is quite nice to see. So let me just give a few examples of Pythagorean representations before we move on. So if you consider the simplest starting module that you can start off with, okay? So we have our P module here. It's just some unit scalars, 1 and 0, acting on a one-dimensional Hilbert space, the complex numbers. And it's quite interesting here that even though we start with a seemingly trivial starting simple object, the Pythagorean representation that we get is actually very non-trivial. So we do get the trivial representation here, but if you ignore that, we also get this quasi-regular representation, which is an irreducible infinite dimensional representation. Okay. So you may say though, okay, well, this is just an induced representation, so that's not too interesting, which is okay, fair enough. So we could make things a bit more interesting. Okay. So we could now consider this P module where now we have scalars 1 over square root of 2. It's still one-dimensional. Okay. And in this case, we now get the Koopman representation. Okay. Again, though, you could say that, okay, well, this is a classical representation. This can be easily constructed without using Jones machinery. Okay. So we could make it slightly more interesting now by now twisting the operators by multiplying by a common unit scalar. So it's still one-dimensional. And this is what I find quite remarkable is that this, from the starting P module, which is one-dimensional, we're actually able to precisely recover the family of irreducible representations from Gantt-Reich. So that's quite amazing that just from this one-dimensional data and this Jones machine or Jones machinery, we can recover one of the 3 families of irreducible representations. So this gives an indication that Jones machinery is quite powerful, and we can possibly construct new examples of irreducible representations of F. And spoiler alerts for anyone who hasn't read the abstract, that is the case, you can, and we'll see that a bit later in the talk. And just to give one more example, this is an example in 2 dimensions, and this again will give us a quasi-regular representation, which is different to the one in the first example. Okay, so just to quickly summarize what we have at the moment. Okay, so one thing that about Jones machinery, which I haven't really said, and it's not really obvious, is that it's very functorial in nature. So we can use a little bit of category theory, not too much, to explain exactly what's actually happening here. Okay, so on the left-hand side here, this is a category of P modules. These are our triples that we start off with, as simple objects. Okay, and this is the space. This left-hand side this is the space that we want to work in. Okay, so it's going to be finite dimensional, and things are quite easy to work in this place here. So given a P module, using Jones machinery, we can obtain a Pythagorean representation of F. Or you can think of this, or more precisely, we actually have a functor here to this category of Pythagorean representations. And moreover, we can extend it to a representation of the Cuntz algebra. And in fact, this is actually a surjection. So every representation of the Cuntz algebra actually comes from a Pythagorean representation or a P module, which is quite nice. And if you think back to what I said, so the whole kind of game we want to play here, the whole kind of goal we want to achieve here is how by just working on this left-hand side where things are finite dimensional, much easier to work with, how can we use Jones machinery or these functors to learn or understand the properties of these complicated representations of F? Okay, so we can actually already say a few things. So there are actually some quite obvious stats that we can say already. So first one is that if we have a reducible P module, so a P module is reducible if we have two subspaces which are orthogonal and are invariant under A and B. Okay, that's what is a reducible P module. Then in this case, our Jones machine or Jones machinery is going to give us a reducible Pythagorean representation. Okay. And as well, if we have equivalent P modules, so if we have a unitary operator which intertwines the operators A and B, okay, so equivalent P modules, this will also give us equivalent Pythagorean representations. So you can already see here that this Jones machinery or this functor does transfer some properties from the left-hand side to properties on the right-hand side. Okay. So unfortunately, though, these are properties that we're not really interested in, though. So we don't want to get reducible representations. We want to get irreducible representations, and also we want to get inequivalent representations as well. So actually, the more interesting questions that we want to ask, and which are much more difficult, actually, is following. So firstly, what we want to know firstly is, do irreducible P modules give irreducible Pythagorean representations? And do inequivalent P modules give inequivalent Pythagorean representations? Okay, so what will be the dream? What is the very best we could wish for is that this functor, this Jones machinery, transfers irreducible objects on the left-hand side to irreducible objects to the right-hand side. And if that was true, that would be amazing, because that would easily give us irreducible representations. Unfortunately, that is not the case. That is too much to hope for. But actually what turns out to be the case, though, is that this actually is true for a large class of these P modules. And actually, for the interesting ones that we actually care about, this statement is going to be true. So we'll see that a bit later on. And just one thing as well, kind of a bonus question we can also ask as well is, how big is this category that we have on the left-hand side of these category of P modules? Because this will give us an indication of how many of these Pythagorean representations can you get using this machinery. So let me introduce just one more piece of terminology. Okay, so we say a P module is diffuse if we take any element in our Hilbert space, and if we continue to apply A and B to it in any order we want, if that sequence goes to 0, then we're going to say it's diffuse. Otherwise, we're going to call the P module to be atomic. Okay. So a Pythagorean representation is going to be atomic if it comes from an atomic P module, or diffuse if it comes from a diffuse P module. Okay. And we have the following nice result. So every Pythagorean representation or P representation can be decomposed into two parts, a diffuse and atomic part. Okay, so that's not too surprising. But what is surprising, though, is that this atomic part is just a direct sum of monomial representations. So these are induced representations. In contrast, this diffuse part will never contain any monomial representations, but it will never contain any induced representations, actually, which is even stronger. So in practice, this atomic part here is not actually too interesting. It's just some induced representations. We don't really care about that. So in most cases, we're just going to discard the atomic part, and we're only going to focus on this diffuse part here. This is where we actually have the interesting representations, and this is actually where all the action is going to be at. And it turns out things are actually quite nice when we just look at these diffuse representations. Okay, so I can say the first main result, which answers the first question I had on the few slides before. So we have a P module, which is diffuse and finite dimensional. Okay, so what we have is that if this P module is irreducible, then the associated Pythagorean representation is going to be irreducible as well. Okay, so this is a very nice result. So if you think back to the picture I had a few slides ago with the functors, this means that if we restrict these functors to only diffuse objects, then this functor is going to preserve irreducible objects. Just by looking at the left-hand side for irreducible objects, which is quite easy using linear algebra, we can straight away obtain irreducible representations of F using Jones machinery. And what we get as an immediate corollary is that all diffuse Pythagorean representations coming from finite dimensional P modules decompose as a finite direct sum of irreducible objects. So I have an example here, but I might just skip past that. just due to time. So and I'll move on to the second result, which answers our second question here. Okay. So now consider irreducible, diffuse, finite-dimensional P modules. Okay, so we can restrict to irreducible P modules now because we have an irreducibility result from the previous slide. Okay, and now the Pythagorean representations are going to be equivalent if and only if the P modules are equivalent. Okay, so again, this is a really nice result because again, this means we only need to work on the Pythagorean P modules, which is just finite dimensional, quite easy to work with. And just from that, we can understand which Pythagorean representations of F are going to be equivalent or not equivalent. Okay. And one thing I should say, so in the previous theorem about irreducibility, I only said it for diffuse representations, but it actually also holds true for atomic representations as well, for very different reasons though. But this theorem here for equivalence does not actually hold for atomic representations. It actually breaks down. So here's actually a counterexample for where it breaks down, but I won't go into the details here. So moving on to the next result. So in the previous two slides, I've shown, okay, well, working with these P modules, we have a really easy way of constructing irreducible, pairwise, non-equivalent Pythagorean representations. You just need to find diffuse, irreducible P modules which are not equivalent. So we can use linear algebra to do that. So next natural question that to ask is, okay, well, how easy is it actually to find such P modules? And actually, the answer to that is there's actually a whole lot of them. And to specify exactly what I actually mean by that, okay, so well, we can define the set here to be the set of irreducible diffuse P modules which have a fixed dimension. Okay, and I want to be fixing a basis here, so I'm looking at the Hilbert space CD. Okay, and we can define a group action of PSUD acting on the set, where we just act by unitary conjugation. Okay, and this is a smooth action, so this is a Lie group action. Okay, and we have the following results. So firstly, given a finite dimensional P module, if I was to pick one at random, okay, if I just pick one at random, almost surely it's going to be diffuse and irreducible. Okay, so this means that it's very easy to find these such kind of P modules. Okay, so there's no need to go looking for them too hard. They're going to exist almost everywhere. Okay. Moreover, this set here is actually a manifold of dimension 3D squared. Moreover, if you consider this group action here, the orbital spaces of this group action is going to form a manifold of dimension 2D squared plus 1. And each orbital space, or each point in this manifold, is going to be in bijection with a set of irreducible classes of diffuse Pythagorean representations of dimension D. So this result really shows you that you actually get a whole heap of irreducible classes of representations from this machinery. So in dimension 1, you actually get a 3-dimensional manifold of irreducible classes, and it's actually S3 minus 2 circles. In dimension 2, you get a 9-dimensional manifold, and so on. So that, yeah, so I'll stop here. I'll just leave the slide up here for you guys to read. Yeah, so thank you for listening to my talk. Happy to take any questions.
Thank you, Dilshan, for the talk. Does anybody have any questions? I guess I have a slightly far-fetched question, which is Ryan's doing a generalization of Thompson groups. Is there any way that you could extend your representation theory results to the Forest-Skene groups?
Yes, that's actually a good question. So that's something that we have looked a little bit into. Haven't done any serious work into it yet. But yeah, you definitely could apply Jones machinery to construct some kind of Pythagorean representations for those kind of groups. And it's quite interesting because in those kind of groups, you do have two colors now. So you kind of have two Pythagorean pairs that you can work with there. But kind of the downside, though, is that you have these Forest-Skene relations. So that means your Pythagorean pair, you kind of go back to the very start. You will need to satisfy this relation. but you will satisfy some few more relations depending on what scheme relation you have when you define your scheme group.
Okay.
So it may be a bit more difficult to find such Pythagorean pairs. But you can still definitely do it if you can find some, and you could definitely define a representation for those groups.
Okay.
So that's definitely something that could be looked at in the future.
Okay, cool. Well, if nobody else has any questions, we can thank Dilshan again.